Hey guys, welcome back to my channel, and I'm really sorry for the previous video. I know the audio quality wasn't very great, so to compensate for that, I'm gonna revise the topics of the previous video in this video. And in today's video, the chapter is gonna be lift, a very important chapter if you ask me. So let's begin with it. So what exactly is lift? So lift is the force perpendicular to the flight path, or also the relative airflow. So what is the flight path? It's the path followed by the aircraft. So if the aircraft is moving in this direction, this is called a flight path. And what is relative airflow? It's the air that we consider it's opposite to the flight path. So this is my flight path, then the relative airflow is going to be in this direction. So they are parallel to each other in opposite direction. So when I say lift is perpendicular to it, it means it's 90 degree to the flight path. And this is a formula for lift: half rho v square CLS. So what is rho over here? Rho is going to be your density. V is going to be your TAS, which is the true speed. CL is going to be the coefficient of lift, and S is going to be your surface area. So a quick thing. So the CL, which is the coefficient of lift, it depends on your angle of attack. Surface area, when I say surface area, it's the surface area of the wings. How big the wings are. The bigger the wings, the more lift they are going to produce. Also, in the lift formula, as I told you, half rho v square CL S. This rho v square. This is also the dynamic pressure, and dynamic pressure is nothing but the indicated SV, the speed you see on your ASI. So for the students who have started their flying, they must know what an ASI is, and for those who don't, so ASI is an instrument where you see your indicated airspeed in your aircraft. So you can expect a few questions on the lift formula. So the lift formula is half rho v square CLS. There could be questions if I double my speed. So if my TAS is twice, what happens to my lift? So if my TAS is twice, which means 2v, and if I square it, that means 4v. So if velocity has become 4 times, that means my lift is going to be 4 times. I hope it makes sense. I'm not going to spend too much time on this topic, but yeah, you can expect questions. And the other question could be what so if I say if density has become twice, or let's say 4 times, what do I do to speed to make the lift constant? So if I make it half, then half square equals to 1 by 4, and then this 4 and this 4 cancel each other out, and your lift is constant. So you can expect questions like this, and I don't want to waste a lot of time on this. If there's any doubt, you can ask me in the comment section. So there's a graph I want to explain to you guys. So there's a graph for your coefficient of lift and your angle of attack. So let's see for a symmetrical aerofoil. Alright, so this is 0. So for symmetrical aerofoil, at 0 angle of attack, your lift is going to be 0. So the graph starts from here. And if the thickness is less, the wing thickness is less, then your lift, of course, your CL is also going to be less. So this is for a symmetrical aerofoil with 6% thickness. So I want to give you a quick explanation of what thickness actually means. So if you remember in the previous video, I told you what an aerofoil is. So this is an aerofoil. This is the upper surface and the lower surface. The more the distance between these two, the maximum is your thickness going to be. So what happens if I increase the thickness? My lift force increases, right? So let's say if there's a symmetrical aerofoil and if increase the thickness, what happens? My CL, I'm sorry, my CL increases. All right. And okay, so I want to explain one more thing. Do you know why there's a sharp decline in the graph? Can you guess like what happens once you increase your angle of attack too much at beyond 16 degrees? Exactly, stall. So this is indicating that your aircraft has stalled and you're no longer producing lift. So your CL is decreasing. So this is for symmetrical. I'm just gonna okay, symmetrical aerofoil with, let's say, 12 degrees, 12% of thickness. Alright. So if you increase your thickness, you see the stall is going to be more gentle and it's going to be delayed. So let's talk about asymmetrical aerofoil with 12% of the thickness. So as you know, that zero lift is at minus 4 degrees for asymmetrical aerofoil. So the graph is going to start from here, and then again this is asymmetrical and it's also 12 degrees. So of course the CL is going to be even more, and this is going to be 12% thickness for asymmetrical. I hope this graph makes sense. This is asymmetrical 12 degree thickness aerofoil. This is very stalling. This is a 12-degree thickness symmetrical aerofoil, and this is a 6-degree thickness aerofoil that is symmetrical. All right. So Yeah, so I want to discuss a few terminologies that are important throughout technical journal. Yeah, so let me change the page. All right, so the first is going to be wingspan. So what is wingspan? So let's say this is the top view of an aircraft. This is my aircraft. This is the wing. All right, this is my elevator. This is my rudder. So the wingspan is the distance from the tip to the tip. So this distance is wingspan. All right, and then root chord. All right, I'm sorry. I'm going to show you root chord. All right, root chord. So it's the length of your chord. So okay, what exactly is chord? I told you, right? The straight line joining the leading and trailing edge. So the length of the chord at the, so this is the root chord, all right? This is the root of the wing. This length is the root chord, and this length, all right, at the tip, it's a tip chord, all right? So there's one more thing known as taper ratio, which is the ratio of tip chord, the length, of course, by the root chord, all right? So this is called the taper ratio of a wing. And let's see, do you know delta wing? Wait, I'll show you a picture for a delta wing. So do you see this wing? This wing. This is the wing. So what is taper ratio? It's the tip chord by the root chord. If you see, the tip chord over here is 0. And of course, this is going to be some value for the root chord. So in this case, the entire equation becomes 0. So the taper ratio over here is 0. And let's say that if there was a rectangular wing, for example, the older aircrafts, if the wing was supposed to be rectangular, let me draw a rectangular wing over here. What would be the taper ratio in this case? It would be 1. Why? Because the tip chord is going to be the same as the root chord, which makes the entire ratio 1. Alright, so the next topic is going to be the next term, I mean aerodynamic chord. It is the average chord length. All right. So as the name is pretty self-explanatory, it is the average chord length of a tapered swept back wing. All right. I know this is quite easy to understand, but this word, what is swept back wing? I'm gonna explain now. Let's go to the next page. All right. So now I'm gonna explain what a swept wing is. So I'm sure you have seen all the modern airliners. This is the elevator again. They don't have straight wings, right? They don't. In what they actually have are swept wings. So the wings are tilted backwards. Do you see? And so the exact definition for a swept back wing or the swept angle is, it's the angle measured from 25% of the chords and are perpendicular to the chord root. So what this means, I'll explain to you. So this is the root chord, right? And this is, wait a minute, I just, yeah, so I'm gonna draw a straight line. Yeah, so this is a root chord and this is a tip chord. So what is 25% from here? If I say this is 25, and for this one is 25, all right? And if I draw a perpendicular from here, from the root chord, all right? And if I join these 2 points, this is my sweep angle. This angle is my sweep angle. I hope that makes sense. So another term or another terminology is going to be dihedral and anhedral wings. So in case of dihedral wings, your tip is above your root. Your tip chord is above your root chord, and for anhedral is opposite. Your tip is below your root chord. I hope that makes sense. And then we have some other term that's called the aspect ratio. It's nothing but it's the ratio of your span. I hope you know what span is, by your average chord, which is mean the average chord I told you about. It's the ratio of these two. All right. So what if I multiply this with the average chord? All right. I multiply this by the average chord. So span, which is this is span, tip to tip, average chord. As you know, the multiplication of span and average chord gives you the wing area. All right. And this becomes average chord square. So this is one more formula for aspect ratio, and there's one more formula. So if I multiply span by span, and also I do the same in the denominator, average chord into span. So what happens? I get span square, but down here, as I told you the formula, you get wing area down here. So this is the third formula. So there are a few benefits of having a high aspect ratio. So I'll tell you one now. It will make sense to you in the next chapter. So if your aspect ratio is high, your drag is less. Spoiler alert, induced drag. But there are a few issues with a high aspect wing. The first one is excessive wing bending moments, reduced rate of roll, and reduced ground clearance during takeoff or landing. So this is actually important. So I wanted to remember these 3 points. So let's move on to the next topic. So yeah, there's one more terminology called the fineness ratio. So I'm gonna draw aerofoil over here. Let's say this is the aerofoil, all right, and this is the maximum length, all right. This is the maximum length, and the maximum width is gonna be somewhere over here, the thickest part, all right. So it's the ratio of the maximum length to the maximum width. So if I multiply these both, I get the finish ratio, which again I hope makes sense to you. So okay, so this is an important topic. All right, wing tip vortices. All right, let's go back. So all right, I'm going to draw an aerofoil, and let's assume there's a tube over here. So if there's air flowing, air flowing, air flowing, air flowing again, so your area. So according to principle of continuity, your mass flow remains constant. So area, density into velocity. All right, so this remains constant, right? But your area here has reduced, so your velocity has to increase. Velocity increases, static pressure decreases. All right, so this is low pressure, and this is comparatively high pressure. All right, so high to low, your lift is generated. This is a brief summary of what we learned in the previous video. Because of audio issues, I've repeated it. All right, so I'm going to draw. This is the aircraft from behind. All right, so this is the APU. Let's say this is the rudder, this is the wing, this is the back view. Okay, so all right, this was the side view, right? This is how when you cut the wing, and then this is the side view. So if I cut this like this and then I see it from the side, I'm gonna get this view over here. So if I see it from the back, even though lift is being generated like this, which is perpendicular to the flight path or relative airflow, do you see this area over here? Don't you think that the air can also travel from here, right? The air can travel from here, right? This is high, this is low. The air is definitely traveling from here. Makes sense? And when the aircraft is moving forward, this produces wingtip vortices, which increases your drag. And this, as you see, as you're creating lift, that's the reason you're creating this drag. Do you remember I told you lift generates drag? Make sense? I hope it does. So there are a few ways to reduce these vortices. I'll talk about them. So the simplest way of reducing this type of drag, which is called induced drag, is by putting a winglet over here. I'm sure you have seen on many aircrafts you have winglets. So this is something you'll learn in the next chapter, and I'll teach it to you. But still, it's good to know information. So this is the way that somehow you reduce it. And as I told you, high aspect ratio means less vortices. But again, these were the disadvantages of having a high aspect ratio, which is important. This is why I told you about it. Now let's go to the next topic. Alright, so the next topic is kind of confusing, but I'm going to make it easy for you. Let's go to the next page. So, do you remember what upwash and downwash is? Alright, so your air, this is upwash, is going on the upper surface and travels, and then it goes down. This is the downwash. Makes sense, right? So, there's something I wanted to remember. Alright, so when you have vortices, alright, your upwash and downwash increases. This increases, alright. So this is your relative airflow. Wait, so this is my chord line, okay? Leading edge, trailing edge, and this is my relative airflow. Opposite to flight path, this is the relative airflow. So what happens when this is increasing? It changes the characteristics of the relative airflow, and it changes into effective airflow. So let's say the relative airflow got changed into effective airflow. I'm going to use some other color over here. Alright, I'm going to use blue. Makes sense? This is the effective air flow. So what is angle of attack? It's the angle between the chord line, which is this line, this one, and your relative F, right? So this was the actual angle of attack, but due to what I said, your upwards and downwards got increased, it became this angle, right? So the lift, which is perpendicular to it, has reduced, right? So what do you do if your lift has reduced? If you see lift equals to half rho v square CL S. So if my lift is reduced, I can increase my angle of attack, right? So if I increase my angle of attack, what happens is my lift moves rearwards. So this was the original lift OG, and this is the new lift because I have to increase my angle of attack to maintain the same lift. So what happens if I increase my angle of attack? Yes, you're right. My vortices increase. All right. So this gives more induced drag. I hope this makes sense to you. So let's go to the next topic. So what is wake turbulence? There's one more topic called wake turbulence. I'll show a pic for this. So basically what wake turbulence is, it's the turbulence created by the passage of aircraft due to wingtip vortices. So do you see? So when your aircraft is moving forward, the wingtip vortices are moving backward, and these give you turbulence, and this turbulence is called wave turbulence. So whenever you think of wave turbulence, I want you to think of a shortcut, which is HCS. H stands for heavy, C stands for clean, S stands for slow. So heavy, clean, slow. When your aircraft is heavy, when your aircraft is clean, clean means no flaps, and when your aircraft is slow, it's gonna create a maximum vortices. Maximum vortices means maximum wave turbulence, which is a hazard. So just remember this HCS, which is max vortices and max turbulence. It's good for your exams. So let's say this is the runway. This is the takeoff path. Alright, you take off like this and you land like this. So let's say when you're landing and an aircraft has already landed. Let's say an aircraft has landed over here and it had some wake turbulence. And you're a comparatively small aircraft. So the thing is, if the aircraft ahead of you is larger, you are gonna get bigger turbulence because of that aircraft ahead of you, just because it's larger in size. So when you're landing behind an aircraft that has created a lot of wake turbulence, what you're supposed to do is you're supposed to touch down after the point he has touched. So if he has landed over here, you're supposed to touch down beyond his point. So this point over here is beyond his point, right? And while taking off, let's say, wait, I'm gonna make a better diagram. So let's say while taking off, this is a heavy aircraft. This is the path he followed, and then he took off. So of course he's gonna leave behind some wake turbulence. So when you're taking off as a light aircraft, what you're supposed to do is you're supposed to rotate prior. So what does rotate mean? That means you pull the control column back and you rotate prior. So this is his airborne. This is this point where he has become airborne, and this is your point where you are airborne. So by rotating prior and by landing beyond, you are protecting yourself from the wake turbulence of the larger aircraft. I hope it makes sense to you. Alright, so the other property of the vortices behind an aircraft is that they can go as far as, so let's say this is, I'm going to draw an aircraft over here. So let's say this is an aircraft, alright. Let's say this is an aircraft, and of course it's going to leave behind wake turbulence. So according to thumb rule, the wake turbulence created by this aircraft can go as far as 9 nautical miles. So let's say this is 9 nautical miles from the aircraft, and it can see, so the property of wake turbulence is that it sinks below. So let's say this is the flight altitude of an aircraft. So 9 nautical miles, it can go as far as 9 nautical miles. And how much it can sink below is 1000 feet, approx 1000 feet. So if let's say you are 35,000 feet, just an example, it can go as low as 34,000 feet and also 9 nautical miles behind your flight path. Make sense? So the other thing I want to teach you is the vortex movement near the ground. Alright. So let's say this is the low pressure, of course, above the wing, and this is the high pressure. Alright. So of course the direction is going to be like this, which is clockwise. This is clockwise direction. Again, this is clockwise, and this is clockwise. And over here it's going to be anti-clockwise because high to low. Makes sense? This is high to low, this is anti-clockwise. So what happens is, this vortices, it touches the ground over here and it tends to move outward. Alright. Now, there's a lot of danger when there's a light, remember, okay, if there's light, crosswind, or light, tailwinds, alright. What is crosswind? Let's say this is your aircraft, alright, from the top view. If you get head-on wind, it's headwind. If you get from behind, it's tailwind. If you get anywhere from the side, it's crosswind. Make sense? So let's say if you're getting winds from here, what happens? This is the upwind vortex, okay? Upwind. What is upwind? It means into the wind. If wind is coming from here, this is definitely into the wind, right? This is in the wind. And this is downwind. What does downwind wind mean? It means opposite to the direction of wind. So what does this do? It makes these vortices stay on the ground, or the correct word would be runway, for longer. So do you see over here? The downwind vortices are on the runway for a longer time, which is a hazard for the other aircrafts. I hope it makes sense. So there's another topic which is very important, and I want to discuss it with you, which is ground effect. Alright, so this topic is kind of important, so I want you guys to pay attention over here. So ground effect. So for the people who have actually flown an aircraft, have done circuits and all, I'm sure when you come for landing, so let's say this is the runway, when you flare, which means you fly straight over the runway, you feel your aircraft is floating a lot, right? You're floating, and then you give your checks to maintain your nose level, right? So why are you floating over here? What does physics say? We're gonna study that. So let's say this is your aircraft and this is your runway. You're coming to land, okay? When you're coming to land, these are your ventive vortices, right? Anti-clockwise over here and clockwise over here. So when you're closer to your ground, do you see your vortices? They're not able to form properly, right? Because of reduced distance, your vortices are not full-fledged form. This provides a cushioning effect. This is a cushioning effect. So when you are in ground effect, what happens is your first of all your vortices reduce, right? So if your vortices reduce, your upwash and downwash reduce, right? Your vortices has reduced, your upwash downwash reduce. So what happens? Your upwash and downwash reduce. Your lift increases, right? So this is basically drag. If this is reducing, your lift is indirectly increasing. That's why you tend to float a lot when you're close to the runway. And if your speed is not on point, and if your speed is higher than how much it should be, definitely it's gonna float more. Why? Because lift is half rho v square CLS. If you increase this more than it should be, you're gonna float even more. I hope this makes sense. So yeah, of course, if your lift is increased and your drag has decreased, your fuel consumption will decrease, your power required will decrease, and all these things are positive. So there's one more thing I want you to remember, that ground effect is most noticeable when the aircraft is flying above the ground at a height less than half of its total wingspan. So this is my total wingspan. Let's say it's 20 meters. Half of it is going to be 10 meters. So if this is 10 meters or less, this is going to be maximum, the ground effect, right? So yeah, so let's say, what if my what if I'm leaving ground effect? So when I'm taking off, I'm basically leaving the ground effect, right? What happens? So see, when you're coming in ground effects, there's a cushioning effect because the distance is reducing. But once you're leaving the ground effect, what's actually happening is your distance is increasing, right? So you're actually giving more space for the vortices to form, right? So this in turn is reducing your lift, so you have to pull back more to produce the enough lift so you can actually take off. Make sense? So when you're leaving ground effect, what's gonna happen? Your vortices increase, upwards, downwards increase, lift reduces, and then again power requirement increases and fuel consumption increases. I hope that makes sense to you. And this is all for the list chapter. I hope you understood all the topics, and if there's any doubt, feel free to message me. And if you're interested in ground classes for DGCA exams, please leave a comment. I'll give you my contact info and we can get started, because I'm seriously, man, this none of the subjects for DGCA are hard. If you give your best and if you actually focus on studying, you can clear all of them in your first attempt. I hope this was helpful.